Attention car shoppers. Right now at South Carolina Federal Credit Union, you can get a new or used auto loan and pay nothing until 2024, and no payments for 90 days means nothing out of pocket going into the new year. Plus, we have flexible rates and terms, so you could make the best financial choice for you. Learn more at scfederal.org/auto loans. That's scfederal.org/auto loans. Certain restrictions apply. Existing South Carolina Federal credit loans are excluded.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you for joining us. This is the Space Nuts podcast with Andrew Dunkley, your host, and of course, Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How are you doing?
I am well, sir. How are you?
Oh, you don't have to call me sir. It's quite all right.
Oh, it's just a thing. It's just a thing I do. I can't help it, you know. It must have been the way I was brought up.
I can just imagine you at school. Sir.
Oh, yes. We had to say sir at school.
Well, we did too.
That was the law. And for the young whippersnappers that are listening in, they had a thing at my school called the cane.
Yeah,
and
I got the cane once.
Oh, I got it a couple of times. I was naughty. And it hurt. It hurt.
Yeah.
We actually had one teacher who had 6 canes and they all had different names.
Oh, dear.
And his favourite was Mark IV because it was the whippiest and it hurt the most. I never got that one. But cruel and evil device. They've been outlawed now. Now, Fred, today on the Space Nuts podcast, episode 231, we're going to look at the Million Star Survey from ASKAP, Changi's spacecraft, Changi spacecraft, which they're looking to touch down on the moon this weekend, Wattle seeds in space. For those who are going, what are wattle seeds? What? They're acacias. That's their genus, I think. And audience questions, we're going to knock off a few of these today if we can. Ralph wants to give his idea of what the universe looks like. Damien is asking about SpaceTime and Dark Matter. Archie is looking at gravitational waves, and Leandro has a really great question. I love this one. Why is there a black hole at galactic centre? I don't think we've ever been asked why there's a black hole at the centre.
Well, why not?
Because it's there.
Because it's there.
All right, we've answered that one. But first, Fred, let's see if we can sort out this Million Star Survey. Is it just been released?
It has, that's right. And it's incredible, actually, what's happened. So this is a story that is about the ASKAP radio telescope array in Western Australia. ASKAP is an acronym for Australian Square Kilometre Array Pathfinder, and it's been operating now in full for probably about 2 years, I think. But one of the things that they have done is to carry out a survey of what you might call local galaxies, but I think these are local in the sense that they go up to several billion light years. And the bottom line is the rapidity with which this survey has been done, because the ASKAP facility is unusual in that these are radio telescopes, but they've got a kind of image sensor at their focus, very like analogous to the image sensor on an optical telescope or on your phone for that matter. These things cover an area, if I remember rightly, it's about 6 degrees square, I think I'm remembering, with pixels in them. And so what you have is the ability to look at patches of the sky and then, record everything that's in that patch. And essentially the bottom line is, just as we used to do with, and still do actually, with survey telescopes in visible light, the bottom line is that you can survey the sky very quickly. And in fact, I think the record that's happened is that they did 3 million galaxies in 300 hours. I think that's total. Let me check that. But that's an astonishing rate of progress for the kind of telescope that we're talking about here. It's really quite remarkable.
That could make it into the Guinness Book of World Records.
It probably is already. That's right.
Maybe.
So let me just check the figures that we've got here. That survey was looking at 83% of the entire sky.
That's
combined.
amazing.
Yeah. That's the sky seen from. Actually, no, that's probably right. 83% sounds a bit. It means they must have gone very close to the northern horizon, but it sounds possible. 3 million galaxies, yes, in 300 hours. And they did it by combining 903 images to make this full map of the sky. Whereas before you'd need tens of thousands of images of the sky with radio telescope surveys. So it's a great achievement. The final 903 images and supporting information is 26 terabytes of data. The images, I think each image contains 70 billion pixels. So it's huge numbers.
Yeah.
Fabulous stuff. It's a great triumph, really, for this radio array, and really puts it on the map in terms of what it can achieve. And of course, there are great things down the track. It's already famous, of course, Andrew, for its work with fast radio bursts, which we've talked about before. The fact that it's this wide angle of view that lets you detect these things.
And I assume this Million Star survey will be a document that will be widely available to anybody who needs it for whatever purpose.
Exactly, that's right. You can already actually, if you probably should Google the ASKAP survey or something, but you can already go to the site that's got a panoramic viewer that will let you actually take a virtual tour of the survey. That's very, very nice. You just sort of scroll around with your mouse, and you can see all these galaxies throughout the sky. It's beautifully done.
Quite amazing. Yeah, I saw some photos, I think it was on Instagram the other day, and I think there was one photo, it says, you are looking at 1 million galaxies. And I went, or was it 3 million or something? Some extraordinary. And, when you first look at it, you think, oh, nice photo of stars. No, they were all galaxies.
Yep.
It's mind-blowing, absolutely mind-blowing. Now, that's good news. The other piece of good news, putting aside China's political tensions and the situations we're talking about in the news at the moment.
We don't talk about that.
No. But Changi 5 is about to touch down on the moon. They sort of did a sneaky launch on us.
In fact, it's already down, Andrew.
Oh, is it?
Touchdown in the small hours of this morning. That's right. Did it successfully. So we've got, another step in this extraordinary mission, Changi 5, to return 2 or 3 kilograms of lunar rocks and soil back to Earth by the middle of next month. It's all happening very quickly, as you said. What really impresses me about this is the technological complexity of this mission. There's many remote dockings and sort of orbital rendezvous and all of that sort of thing, all going on autonomously out there in orbit around the moon. So the lander is down on the moon at the moment. It's built like the old the old lunar modules in the Apollo missions, in that the top half comes back to orbit and the lower half is what allows you to land softly on the moon. It's got a retro-firing rocket to slow down the descent, land you safely on the moon, but then the top half separates and goes back to orbit, hopefully with the samples in. We expect the samples to be gathered within the next couple of days. So watch this space.
How are they collecting them?
There's a drill. They're going to drill a hole in the moon.
I was either going to go with drill or scoop.
Yes, and there's actually a scoop as well. So you drill a hole, then you scoop it up. Yeah,
I can imagine when it all comes back, they'll go, oh, this is so exciting. Oh, it's basalt.
Well, it is basalt, and That is the interesting bit, though, because this is young basalt. The place where it's going is something called Rumker Mons, named after a famous scientist, I think, Rumker, a German word. And that Mount Rumker is basically a young basaltic outcrop. It's about 70 kilometres across. It's big. But the thinking is that this is much younger than the surrounding basalt, and indeed younger than the basalt that was brought back by the Apollo astronauts in the 1960s and 70s. So it's got really interesting scientific outcomes from potentially from the mission. But I think that the technology is perhaps the really astonishing bit, just what an achievement this is.
Yeah, it seems to be, I'm going to sort of understate it a bit, but it seems to be getting easier to do these things. And I suppose after 50 odd years, it should be.
Yes, that's right. There's a bit more, our technology's moved on a bit since the Apollo era.
Indeed,
but it's still a great achievement.
Definitely. Another great achievement that we're going to touch on today is sending Wattle seeds into space. Now, this has got a bit of a local spin on it, this story, but the Giant Leap, the One Giant Leap Australia Foundation has arranged all of this, and a bunch of schools, about 150 of them in Australia, will be sending wattle seeds into space as an experiment. Wattle is a plant that flowers every August in Australia, early spring. Beautiful native plant. It's a part of the acacia variety of trees, and they have the flower is like a little yellow bauble. And they grow them in these massive clusters. And if you're having a good season, all you can see is yellow from, I was going to say something I can't say, from one end of the street to the other. They are just extraordinary trees, quite beautiful, but they're very short-lived, as it turns out, Fred. But one of their great benefits is that they are very good at enriching the soil with nitrogen, I'm told. Which is
that's true.
Which is a great benefit. But this is a terrific story, and one of the schools involved is the Central West Leadership Academy. I work just around the corner from that school when I'm in my other job, and this is a big collaboration. A lot of agencies involved in this one,
including the Australian Space Agency. That's right.
Yeah.
It is. It's great. So the idea is to send these seeds up to the International Space Station, and it's actually a collaboration with the Japanese Space Agency as well, JAXA. That the seeds will basically sit in space for 6 months, then come back to Australia in time for next year's Science Week, which is in August. And basically, what the schools will get is wattle seeds that have flown and wattles in space and wattle seeds that haven't. And the idea is to germinate them and see how they grow and record the data. And I love the catchphrase there, what'll happen to the wattle? Oh, it's lovely.
I've never heard that one before, Fred.
Sheer poetry.
Yes. But it'll be interesting because I think they've done similar experiments with other life, garden life forms before, and there has been significant differences in their growth patterns.
Yes, that's right.
So it'll be fascinating to see what happens to a native Australian plant. And it'll be very exciting for the students. We never got to do this kind of thing when I was at school.
Absolutely.
I think the most I ever got to do was keep silkworms and cut open a dead mouse. That was about it.
Right. Good thing it was dead.
Yeah, it was very dead, and I put it back together afterwards too. I thought that was the right thing to do.
For the next person.
Yeah, exactly. And the scalpel was blunt. It was a terrible job.
Oh, dear.
Horrible job.
Awful.
Yes. But
that's why I did physics rather than biology.
But, I think being able to get sort of involved in sending something into space, it would be a talking point for years to come for these students. And who knows what their kids will probably do in decades to come. I envisage the day that there might be an excursion to a space station. Who knows?
Yes, it's all possible.
It's all possible. Yes. Very, very possible. But good luck to the kids, and can't wait to see the results of that particular experiment. You're listening to and watching the Space Nuts podcast with Andrew Dunkley and Fred Watson. This episode of Space Nuts is brought to you by LastPass, simplifying your online life. Now, if you're anything like me, you probably find one of your biggest frustrations in life is remembering all your passwords, all those login details, usernames, passwords, important information that have built up over many, many years. And you might have hundreds of them. I know last time I counted, I had like 88 passwords for various things, and it can get quite cumbersome. So what can you do about it? Well, I use LastPass. It's a password manager. It's a fabulous solution to this problem. And believe me, the relief is unbelievable, not to mention time saving. Now, you can sign up for LastPass and you'll be joining 25.6 million fellow users from around the world and 70,000 plus businesses. With those kinds of numbers, they've got to be doing something right. And they do. In my experience, it has simplified everything. I've got every username, every password from everything I do built into LastPass. And it's integrated. I can use it on my desktop, I can use it on my laptop, I can use it on my phone, I can use it on my iPad. It's that simple. And it can even work in a way whereby you don't have to type in anything. You open LastPass, you type in what you're looking for, let's say it's your Gmail account or something, and it will bring it up and you just click on the link and it will open it for you. You don't have to do anything. It is really, really good. Now, you can get the premium package for around $4.50 a month, and there's a family and enterprise plan as well, and it works, as I said, across all devices. Put your passwords in, you can go into autopilot, you can reduce the stress. It's really fabulous. I highly recommend it, and it will give you peace of mind. You will never have to sit there going, oh no, I've forgotten my password. It's one of the worst feelings in the world, and this is the solution. It's really simple and highly secure. I mean, it is very safe. All you have to remember is a master password, one password, so that you don't have to remember any of the others. So check it out. Go to spacenutspodcast.com/LastPass and help support the show. Sign up and you can check it out for free at spacenutspodcast.com/LastPass and just simplify your life. Link details are in the show notes and on our website. Now, back to Space Nuts.
Space Nuts.
This is the Space Nuts podcast, episode 231. Andrew Dunkley here with Fred Watson. And don't forget, if you want to watch the podcast, it is now available as a vodcast on YouTube. So just look for, I think it's youtube.com/Space Nuts or Space Nuts Podcast. I can't remember now, but it should be easy to find. All our back episodes are there as well in audio form, but these last few episodes have been recorded in high definition video, so you can watch us do what we're doing, which is basically sitting here talking to each other. It's really exciting to watch people sit and talk, though. I mean, I've done it many, many times. Occasionally, we might even change our facial expressions. But yes, especially when we bump the microphone accidentally, which I've done twice this morning already. But yes, you can watch the vodcast on YouTube, or if you want to socialise with other Space Nuts followers, you can do that at the Space Nuts podcast group on Facebook, and get together with other people and talk astronomy. And it's a very active group. I think there's somewhere around 1,000 or more members of the Space Nuts podcast group. We also have official channels on Facebook and Instagram and Twitter and so many others. So if you're a social media user of any particular ilk, have a look for Space Nuts and you might well find us. Now, Fred, question time. We're going to try and knock off 4 more questions today and do a bit of a catch-up, because we sort of had an avalanche of questions recently. This first one comes from Ralph, and he's in Northern California.
Hello, Big Nuts. I propose that the universe is round. It's finite and round. Perhaps there are others, but ours, at least, is finite and round. There are no sharp edges in nature at the atomic level. Nothing is square. At the cosmic level, round planets revolve in mostly round orbits with round satellites around round stars within primarily round galaxies. Gravity itself dictates a circular motion. Outer shells of atomic structure suggest round orbits or waves of particle neutrons and electrons circling around the proton. The strong nuclear force pulls into the center in a circular way. The weak nuclear force allows escapism to nearby circular orbits. Even magnetic poles display circular attraction from opposing charges. Then there's the circle of life, a circle of reasoning, circular breathing, circle of friends, the color circle, and in music, the circle of fifths. Why should the universe itself be any different? If it all came from a point of singularity, a big bang, and it's ever expanding, and despite the increasing expansion, why shouldn't we expect a spherically round cosmos? On a second note, since time is relative and the speed of light determines relativity, since everything is at a distance except our pupils, then everything is relative. How do we shoot a spaceship to a specific point on Mars when the light coming from Mars is 14 minutes late? Lastly, have you ever considered having special guests on the show? Not that Professor Watson isn't a rock star, he most certainly is. Just an interesting thought for mixing things up a bit. This is Ralph from Northern California. Thanks, as always, to the astronomer at large and the rock star science fiction writer-host, Mr. Dunkley.
Oh, Ralph, thank you very much. I think he's talking us in circles here.
Yeah, look, that's Ralph's first few paragraphs there are a marvelous rhapsody to isotropy, because isotropy, the things being the same in all directions, is basically what he's talking about. And yeah, as far as we know, the universe is isotropic. It's the same in all directions, so you could interpret that as being round. But perhaps the more interesting bit of the of Ralph's rhapsody there is how do we shoot a spaceship to a specific point on Mars when the light coming from Mars is 14 minutes late? That's a really good question. So space navigation is all about exactly this kind of thing, that you have to take into account the fact that there is a delay in signals going out, there's a delay in signals coming back. It's not always 14 minutes with Mars. It depends where Mars is on it, whereabouts Mars is in its orbit. But those delays are taken account of in the orbital calculations, but more especially with a process like landing a spacecraft on Mars, which we all know is very hard. You succeed 50% of the time.
Yeah, that's because Mars is very hard.
Well, it's hard. That's right. It's a hard surface when you hit it. But it's it's always done by aerobraking. You have a heat shield which heats up and slows the spacecraft down. Then there are parachutes and all the rest of it. The bottom line is that's all got to happen autonomously. You can't just rely on, that bit's all right, we'll send the signal to release the parachutes or something like that. It's all got to happen automatically. And that's fraught with pitfalls. The European Space Agency sent it was a test probe, actually. It's about 2 years ago now. It's called Schiaparelli, which was a little lander that was designed to test how their ExoMars lander will go, which I think is now scheduled for launch next year. It's delayed. But Schiaparelli, the software had a glitch in it, so the system thought it was nearly on the ground, so it released the parachute, and it was several kilometres up in the atmosphere. The parachute basically just floated away into the wide blue yonder, and this thing hit the ground rather faster than it was supposed to. So everything's got to work. Yep.
Yeah.
But great question from Ralph. Thank you very much.
Yeah, of course, that's all very complicated. The simplest thing to do would be to just hit the launch button 14 minutes, before the zero count.
Well, yeah, that's right. But then you don't find out for 28 minutes whether you've done the right thing or not. Oh, possibly. Too soon. Yeah.
Oops, missed that by 1 second.
Yeah, that's right.
Or as Get Smart used to say, missed it by that much.
Exactly.
Yes. All right. Ralph, thanks for the question. We'll go now to Damien Huxley, who's got a question about something we've never, ever discussed before.
Oh.
Space-time and space-time and dark matter.
Question about space-time and dark matter.
There you go.
When we calculate the mass of the sun and the planets, does Newton's laws of gravitation and Einstein's equation of space-time take into account dark matter? I guess not, since Newton didn't know about the dark stuff. So does that mean there isn't any dark matter in our solar system? Or it is included in the calculations? Then, dark matter is 27%, and normal matter is 5%, is the sun, Earth, and us, mostly dark matter. Thanks, guys, for a great show. Damien Huxley.
Thank you, Damien. Gosh, the old dark matter question again, Fred.
But it's great. These are the really good questions about why it is that there's only certain ways that we can determine how dark matter behaves. We still don't know what it is.
Yeah.
And I think we're kind of possibly closing in on the. Well, it's actually maybe even too optimistic.
You know what they'll find out, Fred. They will, and I've got personal experience with this. They will find out that all golf balls are made of dark matter. That's why they're invisible.
Yeah,
we can't hit them.
So it's because of the way galaxies behave that we believe dark matter is a reality. It's something that is present in the universe. It only reveals itself by its gravity. It doesn't shine, it doesn't block light out, so it doesn't really interact with photons and, in fact, with anything else, the other normal, the normal makeup of matter.
It's nonconformist.
Nonconformist, or you could call it exotic. That's the word.
That's a better one.
And, I mean, it's mixing metaphors, that. I suppose there are some exotic Methodists out there, which is, what you'd get to. Anyway, the bottom line is that dark matter, certainly in our galaxy, is everywhere, because that's how galaxies are made, how they're put together. But it's distributed over very wide volumes. And so if you've got a solar system that's immersed in this stuff, and it's uniform throughout the solar system, which we believe it is, then that's how Newton's laws can work in such an environment, because the dark matter itself, being just a kind of uniform background, doesn't have any effect on it. It's only when you get to galactic scales that you start seeing the fact that galaxies, they must have dark matter because they're otherwise rotating too quickly. So you can, yes, dark matter, we believe, is there, and it's approximately those ratios that Damien mentioned. 27% of the component of the universe. So it's roughly, it's kind of roughly, dark energy is 75%, dark matter's 20%, and normal matter's 5%. That's not quite right, but it's that sort of, that's the mass energy budget of the universe, because mass and energy are equivalent. So that's the thinking. But there are scientists, and I suspect in a way it's an increasing number, who are getting frustrated by the fact that we're not detecting what dark matter particles are, and they're looking for other ideas. Mordechai Milgrom was very early in this, in the 1980s, suggesting his theory of MOND, modified Newtonian dynamics, that suggests that gravitation doesn't quite work at the low accelerator, or the laws of motion don't work at the low accelerations that we see. That's not. It doesn't work because you lose other things if you put that in. But there are some people who are looking at new and unusual forms of hydrogen, newly thought about unusual forms of hydrogen. And so it's possible that over the next decade, our thinking might turn around completely on dark matter. And it might be, it's hydrogen, but a different sort of hydrogen. That's very much, it's very controversial, is that, and certainly a minority view. But I've seen a number of papers recently that are looking at that. So watch this space.
Yes.
It's certainly something out there.
Watch 95% of it,
yes,
anyway.
That's right. Well, actually, the 5% that we can see.
Yes, well, that's all we can see.
Yes,
and that's where it gets so extraordinary. We can see all of this stuff, this amazing stuff around us, and it's only 5% of everything. I mean, that's the mind-blowing part of it.
It is. It's unbelievable.
Yeah, quite extraordinary. How long, ballpark figure, and this is a question without notice, but how long do you think it will take, if ever, for them to crack the dark matter and dark energy puzzle?
So I think dark matter, the two are quite different, Andrew. They've got similar names, and that's really bad. They should, one should be given a different sort of name. Dark energy is what we think causes the accelerated expansion of the universe, that there's an energy of space itself that's pushing the universe apart ever more rapidly. And we really don't know what that is. That's quite a difficult problem to crack. I think that is the one that will take more than 10 years, maybe 20 years to figure out. Dark matter, I'm more optimistic of. I mean, I'm a bit less optimistic than I was a couple of years ago, because the big theory for dark matter was supersymmetry. That was the idea in physics that every subatomic particle has got its supersymmetric shadow particle, which we don't see because it's hidden in some hidden dimension. But the Large Hadron Collider has explored the energy levels that people have thought you might see supersymmetric particles, and there's nothing there, up to 14 tera electron volts, which is its operating energy. So either these things are more massive than we thought they are, or supersymmetry is wrong, and that's why people are looking at other ideas.
Yeah, well, it helped. It's good to look outside what you think is right, because you might be wrong, and therefore.
Exactly. Well, that's how science works.
Yes.
You keep your mind open, especially if it's a puzzle like this.
Well, a lot of the time it's based on theory, and you do experiments to prove the theory right or wrong. And if it's wrong, well, you come up with something else and try again. It's sort of like playing darts. You just got to keep going until you hit a bullseye.
Or whatever you're trying to hit.
Or whatever. Yes.
Yeah.
See what you've done, Damien?
Yeah, it's all Damien's fault.
It's all your fault. No, but thanks for the question. Very, very good. Yes, we will watch with interest. We might just have to hold our breaths for a very long time before these issues are solved. This is the Space Nuts podcast. Andrew Dunkley here with, of course, Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Thanks for joining us on the Space Nuts podcast. Andrew Dunkley and Fred Watson, of course. Always good to have your company wherever you are, whenever you are. Of course, you can visit the Space Nuts website, spacenutspodcast.com, and you can do a lot of things there. Of course, there's the Astronomy Daily tab where you can catch up on all the astronomy news that's going around at the present time. That gets updated so very regularly, and you may be on the email list, and if you're not, you can certainly sign up for it. There's the Space Nuts shop where there's lots of goodies that you can get for Christmas. The Space Nuts mugs. That's not me and Fred. That's actual mugs. There's also Space Nuts shirts, polo shirts, stickers, caps, etc. There's the Space Nuts bookshop and so much more. So check us out at spacenutspodcast.com if you'd like to just have a look around. You don't have to buy anything, but we'd really like it if you did. But yeah, you don't have to buy anything. And if you do want to contribute to the podcast, you can do that through any of our patron-like websites, patreon.com and Supercast. Check them out. You can do that through the website as well. There's package deals through Supercast, or you can just choose what you think's a fair amount to pay us on a monthly basis. At your leisure on patreon.com/spacenuts. But again, not mandatory. We're never going to tell you that it has to be done. So just something to think about. Now, we've got another question. Fred, this one comes from, I think it's Arke in Sweden. Let's see what he's got to ask us.
Hello, my name is Orchia and I'm from Sweden. I'm a keen follower of your show. I have a couple of questions regarding gravitational waves. How can we be sure that gravitational waves that we detect originate from the collision of black holes and not something else with large masses? Also, can we determine the location of the collision or at least the direction to it? Thank you for a great podcast.
Okay, thank you very much for your question. The answer is yes and yes.
It is. I think maybe Orca wants a little bit more than that, but that's
I thought we covered it. I thought we covered it pretty well.
So, look, it's a great question, actually, and I'm very glad it's come up because I don't think we've really explained this that carefully. We now have more than one gravitational wave detector in the world. The operational ones are the LIGO, the Laser Interferometric Gravitational Wave Observatory, which has 2 facilities in the United States. Virgo is another one in Italy. I think there might be others coming on stream as well. India and Japan ring bells with me, but I'd need to check on that. But so just going to the last part of Orca's question first. How can we determine the location of the collision, or at least the direction to it? Yes, the direction is better pinpointed when you have more detectors because you can sort of triangulate. Excuse me a moment. Sorry about that. Sorry, Orca. Sorry, Andrew. Coughing into the mic. So you know, the more detectors you've got, the better your ability to determine the direction that it comes from. And sometimes these things have essentially an electromagnetic counterpart as well. And of course, if you can pick that up with a radio telescope or an X-ray telescope or even a visible light telescope, then you can pinpoint it much more accurately. Going back, though, to how you know what it is that's colliding, it's really remarkable the way this is done, because when 2 objects, let's talk about black holes, for example, when 2 black holes collide, they don't just sort of charge into one another. They basically start off in an orbit around one another, which gradually gets smaller. They're mutually. Actually, I'm on video, aren't I? So I can do the hand motions.
Yes, you can.
They're virtually spiraling inwards, and as they spiral inwards, just as my fingers are doing there, they get faster and faster until they merge. And that process is what releases the gravitational waves. Now, what you see in the gravitational wave signal is it's essentially a wave which gets more and more rapid in frequency. So you've got this wave whose frequency is increasing, and that gives you 3 parameters, Andrew. It gives you, first of all, the frequency of the wave, the amplitude, that's how much the gravitational field is shaking, and the rapidity with which it's increasing. In other words, the sort of acceleration as these 2 objects come together. And those 3 things are what let you tell what it is. It gives you the masses of the colliding objects. Once you get to anything above, say, 10 to 20 times the mass of the sun, you know it's going to be a black hole, because that's what it has to be. You know the size of it is very small from the 3 parameters that I've just given, or the size of the colliding objects. So you can detect what it is, a black hole or a neutron star. And that's raised puzzles, actually, because it looks as though there are neutron stars that are more massive than we thought they could be, because they've been registered by these collisions. But it's an intriguing process, and it's done by very accurate computer modeling.
Very good. Okay. Thanks, Orca. I hope that answered your question. Now we've got a question from Leandro in Argentina. Hello, I discovered your podcast some months ago and I liked it immediately. Well, that's a first.
It's great.
It's really easy to listen to and extremely enjoyable. Well, thank you. I started from the first episode and I don't remember exactly where I'm at now, but I keep listening in a nice half hour of cool stuff and hosts. I usually start my day listening to you. That's lovely.
Yeah, that's
I think I have a kind of comment and question at the same time. I usually hear scientists talk about the existence of a black hole at the center of almost every galaxy, but I've never heard them explaining the reason for this. So I started thinking that the center of a galaxy may be the place with more mass in it, And when you have a lot of mass concentrated in a reduced space, that may form a black hole in time. Well, that's the answer I got. And related to this, and as far as I know, our sun is responsible for all the planets in the solar system to stick together and not wander around. It's gravity, and I heard Fred some episodes ago saying that they think the black matter or dark matter is responsible for keeping the Milky Way as it is and not getting spread out. That means the black hole at the center of the galaxy is not able to maintain gravitationally together all the bodies in our galaxy as our sun does with the solar system. That's it. Hope it wasn't too long. I'm going to take a breath now. Thanks for every episode. Lots of fun and good information. Well, he's referring to something we probably said a couple of years ago.
That's all right. That's quite all right. It's a great question, and actually, Leandro's question is one that astronomers themselves ask. Which came first, the galaxy or the black hole? And the thinking is that the black holes, partly because of the high density of matter in the center of a galaxy. It's all about the way matter collapses on itself, and this is now in the early universe. That high density of matter, some stars which would have been very high mass stars, they blow themselves up and end up forming high mass black holes in the early universe. And the thinking is that there were collisions, just like what we've been talking about with Orca's question there, that black holes collide, they make bigger black holes, and over time that means that you grow supermassive black holes. So it's an accretion process. The galaxy and the black holes may well have formed together, but the black holes grow within the centers of galaxies, and it's not that well clarified. It's not that fully understood, but that's the thinking. It's we know that galaxies grow by gobbling up smaller galaxies. Our own galaxy's done that. We've seen evidence of that. Some of the work I've done in the past has pointed to dwarf galaxies that have been gobbled up by our own galaxy, and so that's how galaxies grow. And the thinking is that the black holes grow simultaneously or concurrently with that in the centers of the galaxies. Just going to the last part of Leandro's question, it's actually yes, he's right. Without the dark matter in our galaxy, it would fly apart. That's absolutely true. But it's actually not the black hole in the middle that's the main gravitational body that's holding it together, apart from the dark matter. It's the whole galaxy. So our black hole in the middle of the galaxy is for about 4 million solar masses, but the galaxy itself in normal matter is about 400 billion solar masses. So it's all of that, that concentration of matter that keeps it together, but it's not enough. That's why we have to have dark matter as well.
Okay, very good. Thank you, Leandro, for your question. It's prompted a question in my mind. We know that our galaxy is ultimately going to merge with Andromeda. Does that mean ultimately their black hole and our black hole will crash into each other?
Probably. It may take some time because that collision will, they'll pass through one another and then they'll come back. It'll be a long, drawn-out train wreck. But at some point down the track, the black holes will probably merge. That's right.
What would be the effect
of the train wreck on us? Not that much, actually, because there's so much empty space there. The sun will probably not collide with any other star. There will likely be a burst of star formation, so there might be supernovas going off that are a bit close for comfort. But generally speaking, it's not as dire as people might think.
Well, that's good news.
Yes, it's good news. That's right.
Because I just bought a new car. No, I'm kidding. I never bought a new car.
You can't afford a new car.
I can't afford a new car. Definitely not. Thanks for the question, Leandro. Now, we've got one more thing to do before we finish up today, and it's a follow-up to a question from Snow in New Zealand last week, and he's just sort of I guess, taken us to task on something. Hey, Fred and Andrew, thanks for answering my question about the Earth's magnetic pole. I understand about the compass south needle marked as north, but if you float a magnet on a cork, as you mentioned, the North Pole at the magnet points towards the North Pole of the Earth. I've done this with an industrial magnet with the poles marked and have checked their magnet with a halo effect transistor. Or Hall effect.
It's Hall effect.
Hall effect.
Yeah. Hall effect.
To make sure the poles are marked correctly. The only other thing I can mention, and don't know where does the positive charged ions from the solar wind go, north or south magnetic pole of the Earth, to create the northern or southern lights? Thanks again, Snow from New Zealand. He's really putting a lot of thought into this.
It's fabulous. And he's right, too.
It's kept him awake at night. I know that.
So, Snow, you're right, absolutely right. So I got it the wrong way around when we were talking last time about this. I said that, the North Pole of the Earth pulls magnets, the compass magnet to the north, because really the North Pole of the compass magnet is actually the South Pole, but it's the other way around. The North Pole, the North magnetic pole of the Earth has the polarity of a South magnetic pole. Work that one out. What we've been calling the North Pole forever, it's only called the North Pole because it's in the north, but it's actually a south magnetic pole. And then the other issue with the positive and negative ions, we're talking there about electrical charge rather than magnetic charge. So they all stream down the magnetic field lines of the Earth. That's how we get the aurorae. Both the electrons and the protons beam in towards the poles. They do it in a rather complex way, but that's what happens.
Fantastic. All right. There you go, Snow. You were right.
Yes, he was. He was right.
And it's all good. We stand corrected, and we're happy to do that. Actually, because he's come back to me, I was going to tell a story last week, and I completely forgot. But we talked about making compasses out of needles and corks and floating them in water. I did that as a kid. I remember one Sunday morning, Mum and Dad were still in bed, and I thought, I'm going to have a crack at this. So I got a magnet, and I magnetised one tip of the needle, and I stuck it in the carpet, and I went and got a cork, and when I came back, I just planted my hands on the carpet, and the eye of the needle went right in there.
Gosh.
Didn't hit the bone. Didn't come out the other side. But, and you know what? Didn't bleed, which says a lot about me.
But your blood's magnetic, probably.
Yeah, and it missed the nerve, so I didn't even feel any pain. I just went, ah.
Yes, I bet you did.
Pulled it out. It was just one strange thing. Yes, great way to finish. Although a couple of times when I've given blood and they've put the needle in, this is really freaking some people out, I suppose. But I haven't felt it. So there must be gaps in the nerves in the human body. So if you can find those, that's where you stick the needles in.
Sounds good.
Yes. Enough of that. Thank you so much to everybody who contributed all those questions. Keep them coming in. Don't forget you can send your questions to us via text service through our website, spacenutspodcast.com. There's an email thingy there. That's its official name, email thingy. Or you can click on the AMA tab and record your question. Don't forget to tell us who you are and where you're from, and we'll get as many answered as possible. We've been doing a bit of catching up of late, and it's good to be able to do so many questions and hear your voices. Thanks again. And thank you, Fred, as always. Great pleasure. Good to see you.
Yeah, you too. We'll see you next week.
Indeed, we will. Fred Watson, astronomer at large from the Space Nuts team, and from me, Andrew Dunkley. Thanks again for listening. We will catch you again real soon. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.